And you want to record this session?
Yes, that's true. Record. I think we have it. All right, I think we're good.
Hmm.
Let's just wait a little bit and then we do intro. Yeah. All right, hello everyone. Welcome to another episode of Quirkcast Weekly Science News. This is your host Tim.
And I'm Mikey.
And this is Sahil. Welcome everybody to a brand new episode of Quirkcast, where we review various news articles and give you the down low on them, or the lowdown, or however you want to say it. So, if you haven't already, do join our Discord channel so you can ask us questions there and we can get to them. And if you're watching this on YouTube Live, feel free to ask any questions that you have, and we'll get to them during the episode. So, without further ado, Tim and Mikey, let's jump into it. So, I was reading this article by IFL Science, if I'm not mistaken. I was talking about this number, a special number 137, and how it's very unique in physics, and it appears a lot in lots of equations for chemistry and electrodynamics. So, I guess my question for you, Tim, is this number actually very special, or is it full of hot air?
Yeah, so why don't we just go to the article and see exactly what Sahil was talking about? Um, is this article, and I think I've seen quite a few that are similar to this. For instance, this one from IFL Science says the most important number it's 137, and this is why. Uh, so this is the title, and immediately jumped to my mind is that I know that this is referring to what we call the fine structure constant, which is not really 137, but it's approximately 1 over 137.035, blah, 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 blah. Okay, so they're referring to this particular constant. Um, Whether it's special or not, I think it depends on your perspective. So, what do you think, Mikey?
Um, I think just the first offense is that um, they mentioned the word 130, they mentioned the number 137, but as you mentioned, the actual number that people measure in chemistry and whatnot is 137 point blah, 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 blah. It's like a decimal number. So there's absolutely nothing special about the integer 137. That we can say for sure. So the question is, how special is it? Um, I guess compared to what, right? Like people have been looking, people like the idea of special numbers, right? Like beauty, like beautiful numbers that arise everywhere. People get the sense it's like God's pattern,
Right,
leads
yeah.
to like Freemasonic beliefs of like sacred geometry. So like, pi's up there, right? Like everyone would agree that pi is a great
Mm-hmm.
number, special number. Exponential e, like 2.7, whatever. That's like a very special number. What about with respect to that?
Yeah, I think on some level, if you follow the article, you can read through the argument why that number is special. So that number is what we call a coupling constant, and it kind of tells us the strength of particular interactions. And the reason why the article claims that it's such an important number is because the way chemistry works, for example, the strength at which electrons orbit around the nucleus, it's dictated by this number. And things like chemistries and how charged particles emit light. All the formula has to go through this number. And but actually I don't like to call it the number. Let's call it the fine structure constant alpha. Right? It goes through this numerical number. So to that extent, yeah, I think it is important. But back to Mikey's point, I don't like to refer to it as a number because that's not how physicists really think about it, right?
What What do you mean? It isn't it a number though? Like 1/137 point something something something.
Right. I think it's better to think of it as a parameter. It's kind of like um, it has some value, but we wouldn't be that surprised if the value of it is a little bit different. even though our
It is essentially
yeah,
the strength of the electromagnetic force, right? You
exactly.
can imagine that every single force has some number that determines how strong it is. The gravity is weaker than electromagnetism, and that's because this number that determines their interaction strength is larger for electromagnetism than it is for gravity. So, I mean, it is. Is it a number? um,
Yeah, I think to me it wouldn't be a number because I can imagine a universe in which this parameter, I like to call it, is different. Certainly, chemistry in that universe will be very different, but that universe doesn't just become like unviable. It just doesn't become like a crazy universe. Like it wouldn't be that crazy to have a different universe with slightly different fine structure constant. So I think that's why this is a little different from numbers that a lot of times people refer to. Like the number four, we have four dimensions, right? That's that's like a more special number, I would say, because if it wasn't four, like things will be really different, right? But if this so-called fine structure constant is a little different, you know, the overall structure of the universe won't be that drastically different.
So I guess one question that I have is why would this parameter change even in this universe, or like how can you get it to change? What does that even mean?
well, you have to remember this is the literally the measured strength of the electromagnetic force,
Hmm.
and so it actually depends on how close you're looking. Um,
Mm.
so this is just 137 just happens to describe the value of this interaction strength at a particular distance. But even in our universe, if you zoom in, the effective strength of this interaction changes. So it's not even like a anything. It's nothing like it's not even to say it's not a constant. It's not even something that's meant to be consistent in any way or in
Yeah.
any way related to the number 137.
So Mikey, can you give an example? What do you mean, like if you zoom in closer? Like how does the strength of electromagnetism change as you zoom in closer?
That's a good question. So it's an interesting question. So like if I just look at uh, an electron standing by itself, right? I can
Hmm.
ask, what is the strength of attraction between me and that electron,
Hmm.
right? And um, as I get closer to it, I feel the strength of that attraction increasing. But the question is, how much, like, how strong is that force as I get closer to it? That's what this number determines. But as you get closer to the electron, um, there's actually quantum mechanics creates like it's called a shielding mechanism. You actually create particle antiparticle pairs out of thin air because of the energy that's involved there. And then your actual attraction to the original electron actually starts to go down.
Hmm.
So you think as you get closer to the electron, we learned that the force is inversely proportional to the distance squared away. So as you get closer, you feel the force more strongly. But there's actually a certain point where the strength of that interaction drops because of quantum mechanical shielding effects. So that is literally goes into the number alpha. You would actually say that the value of alpha has this number 1 over 137. It's not 1 over 137 anymore. You actually measure it to be something else.
Yeah,
So it's
I think it gets stronger, right? But the sign oh yeah, it depends on what you mean. As you get
the point
closer.
is it's a dynamic quantity.
Right.
So to say that there's something special about a particular value of it is very,
Yeah.
very silly, I think.
Yeah,
Yeah, applicable.
yeah, because it depends on the way we measure it. So there's some human component to it. We have to define a convention by which we measure this value, and then it's going to show at 137.01 over 137.03599 whatever, right? So I would say as physicists, we shouldn't. I mean, people have tried to obsess over these values, but it's not very fruitful, right? So I think
Not only is it not special, but it's not even um sure, I had a good word. Darn it.
yeah, it doesn't deserve an explanation. Let's put it that way.
It yeah. not only is it not special, but it's actually arbitrary.
Yeah, exactly.
Got it, got it. So, what is your final rating for this article? Yay or nay for reading it? Mikey, go first.
I think it's kind of like trying to entice people who like to believe that there are like beautiful numbers and some order in the universe. And so for that reason, I think it's actually very nefarious because it's like kind of um, infecting people through like their best intentions. So I would say that this is like a red flag, avoid. Like if you're looking for something really deep about nature, you don't want to be one of those people who goes around thinking that 137 is like a magical integer. There are people like that. And yeah, this article is just kind of like pulling people in a pretty bad direction.
Gotcha. How about you, Tim?
Yeah, as for me, I would say I would say there's some good bit of information in there if you're looking to understand what this number does, what it controls. So there's a good bit of info there. But I would say just be highly cautious with what the title is claiming, that somehow there's something magical about this number. There isn't. I mean, there's just is a number that somehow is related to many things. So just marvel at that fact, but don't get carried away with the point it's trying to get across. So I would say you can probably pass the reading if you don't want to, but if you want to find inspiration about some of these physics facts, read but proceed cautiously.
Fair, fair. All right, let's move to our next article that I'd look at. So this article was about the elusive neutrino particles, and in particular, there was something strange and anomalous going on with them. I thought this was rather a bit more complicated. So I guess Tim, could you break it down? Like, what was this experiment all about before we describe what the experiment was?
Right, exactly. So this is actually a recent news from an actual experiment, physics experiment, and you can find it from Science Alert or other news source. For example, this is the title from Science Alert. It says, "A very exciting anomaly detected. A major experiment could be huge news for physics." And of course, Sahil, you're right that there isn't that much information being conveyed in the title, and you definitely, there's some buzzwords there, things like neutrinos, big experiment, huge deal for science potentially. You're right to be skeptical, but in essence, what it is there's an experiment called the BESS experiment. I think it's the Balkans. I forgot what the E stand for. Some neutrino telescope experiment. They find something slightly unexpected in their experiment, and this could be indicative of a discovery of a new particle. Um, so, so actually, as a physicist, when I dig a little deeper in this title, it actually seems like there's something to offer there. This seems, and there's also a paper that is linked in the article. So something is actually interesting going on. So from initial read. So what do you think, Mikey? I'll pass it on to you.
Yeah, I mean, it's there's a lot of articles you see about like, oh, a new discovery is going to completely change the way we think about everything. And typically, obviously, if it's a article with a title like that, you can kind of tell it's sensationalist, probably overhyping a lot of stuff. This is like, you know, you see some of that here trying to hype up this result, but I think this kind of smells like it has like some real potential. This is like actually one of those things where, it's going to be a while before we know, but it's possible that we will say that this was the first time we realized that our universe is connected to a hidden, dark parallel universe, essentially.
Yeah, maybe it's worthwhile to break it down exactly what this news is about, right? So there's basically there's an experiment in some mountains in northern Russia. I think it's Quirkcast Mountain, probably butchering the name. It's deep underground. What they're trying to do is they're trying to study neutrinos. And neutrinos are very elusive particles. They don't like to interact very much. So in order to really see them, you need huge amounts of material. So what they do is, I think they use, I was reading into it, as an interesting experiment, they use chromium, which will naturally decay once you shoot some neutrons into it. And when they decay, you know for a fact that they will create neutrinos, right? But then surrounding the chromium, radioactive chromium, is a bunch of chemical agent like gallium and whatnot. Yeah, and the hope is the gallium will absorb these neutrinos at various distance from the source and convert into a detectable signal, right? So at the end of the day, what they're doing is they're trying to create some number of neutrinos, and they're trying to redetect those number of neutrinos to see if the numbers are consistent. It seems like a pretty straightforward, experiment. You make something and you try to verify what you made is how much you've made, right? But what's interesting is instead of finding 100% what they created, those neutrinos, they only found about like 75%. Something is amiss. And that actually has been observed previously in other experiments with similar setup. So basically, this experiment is a validation of what we call an anomaly. Something unexpected is happening when you make neutrinos. They seemingly just kind of disappear out of nowhere. So that's why this is the essence of the experiment. This is why this is kind of a mystery right now. And we're not sure what to make of it. And that is interesting news indeed.
So are you saying that they did an experiment with detecting neutrinos, but they found far less than they would have expected?
Exactly. They try to calibrate with the errors. So there's a very legitimate article with very good physicists carefully studying, and this experiment could have been really boring, basically. Let's say they make 100 neutrinos, and they successfully detected almost all of them, or whatever, or you can't detect all the neutrinos, but let's say you detected 50 and you expected 50. End of story. That would have been a really boring experiment. Like, oh, nothing is found. We made 100 neutrinos, and we confirmed that we probably made around 100 neutrinos. No biggie, right? But there's a discrepancy here. They make something, and some of these neutrinos gone missing. So now the theorists can come in and be like, scratch our head. Maybe this is why there's this kind of clickbaity title. Maybe some of these neutrinos actually turn into something new that we cannot see. Of course, you cannot see it, so you don't know what those are. But that's a plausibility. We don't know yet. We cannot confirm yet. So that's exciting, I would say.
I see. So are you saying, so what's an example of something it could be or postulated in your mind?
Neutrinos are kind of cool because, like, among all the particles in the universe, like, most of the particles are things that we can, like, even hope to interact with. But neutrinos, they're almost like, they almost exist in like a parallel universe. Like, huge numbers of neutrinos could be flying through your body, but they don't interact with anything that we interact with. So they essentially just pass through like ghosts. And because neutrinos interact so weakly with normal matter, like, we can't detect, they're so hard to detect, they're so hard to like verify, you can't keep track of them. So one of the lines of thought that, like, theorists have been on for a while is that neutrinos could be like bridges to kind of like a dark parallel universe that's like sitting right on top of us, but we would never know it because, though that world doesn't interact with us at all. Just, there's no physics connection between the two. Because neutrinos are kind of like that to us, they kind of open the idea of this possibility that there are these, like, a whole bunch of stuff out there that we don't know about. And these are where theories of dark matter typically come from. So if you see an anomaly in a neutrino experiment, it could be nothing because they're just really hard to detect. But if it's something, it's probably something really exciting.
Yeah.
Mm.
Yeah, and then some of these particles we can call sterile neutrino. But I guarantee you the actual concept is more exciting than the word suggests. The word suggests something like a new type of neutrino, but that's less interacting. But really, what it means is this is just a totally brand new particle that we have not seen at all. But it doesn't look so exciting because it doesn't interact with us. But it could interact with many other things, including things like dark matter, and there's a whole host of like dark sector particles. So it's just a exciting but yet big unknown. But we don't know yet. So
Huh. To kind of take like a little bit of a off tangent sort of question, could you use any gravitational detectors on this sort of stuff to maybe detect if it has some effect? Or
Nope.
would that just
Not
be,
not not only are neutrinos so weakly interacting with us that we can't even detect them through like contact. They're so light that there's almost no there's just the ideal thing that's hard to like detect.
yeah, that's true. It's really hard to detect these guys, and experiments like these might be one of the only portals we can kind of look in and take a look and see what's going on. I mean, there might be other ways you can measure the universe to see if there's something amiss, but those are very different sort of experiments, and you don't. There's no guarantee that you can find them anywhere else, basically.
I see. So uh now coming back to this article, how would you both rate it? Mikey, what's your say?
Yeah. So if you're like a fan person of like scientific results, like you see in the news, people say, oh, this could be like could result in a revolution, could be a big new breakthrough. Um, this is the kind of thing where it's like kind of stays on your radar. Like as a physicist, like if I see an update about this, I'll remember this original article because there's a very reasonable possibility that this could go somewhere interesting.
Hmm,
It's not like total nonsense. So it's a little technical and requires kind of like someone who's well versed in the subject, but it's something to keep an eye on. So I'll say it's good.
gotcha. How about you, Tim?
Yeah, I would say definitely worth a read, even if you're not maybe technically inclined. Unfortunately, good science articles are just a little more technical sometimes, and a lot of times they're, I mean, sort of ignore the clickbaity title, but a lot of these scientific results are very nuanced, right? Like because there's so many unknowns, we don't know what they could be. Maybe the experiment calibration was a little off. Maybe this is nothing. But with all these caveats in mind, this is literally scientific progress in the making right now. It's not as flashy as some of us might hope, but this is this could be history in the making a few years down the road. So I would say, yeah, take a look, take a really careful look, carefully read it, see if you can understand it, and this is a good article. But don't get too carried away with the title, because to discover a new particle, new sterile neutrino, I won't hold my breath. It might take a while.
I see. So this one's approach it, but approach it cautiously is what
Yes.
what I'm hearing. Gotcha. Well, I think on that note, I'd like to thank everybody for joining us, and we'll see you all next week.
Yeah. Thanks everyone. See ya.
Yep.
Bye.
See ya.